For our first warm-up exercise, we want to know what points on the curve sine theta minus 1 lie in the third quadrant. We know that when r is greater than 0, the point r theta lies in the same quadrant as theta. In other words, if we had the point 1 pi over 4, it would lie in the first quadrant. When r is less than 0, then the point r theta lies in the opposite quadrant as theta. For example, the point negative 1 pi over 4 lies in the third quadrant. That means we need to know when our curve, sine theta minus 1, is positive and when it's negative. We know that sine theta is bound by negative 1 and positive 1. If we subtract 1 from both sides of this equation, we get that negative 2 is less than or equal to sine theta minus 1 less than or equal to 0. And since sine theta minus 1 is our r, that tells us that r is going to be less than or equal to 0 for all theta. That means the values of theta that lie in the third quadrant have to come from the opposite quadrant. Theta between 0 and pi over 2 gives third quadrant points. We know that in polar, we can express any point in 4 different ways. For our next example, we want to know another way to describe the point 3/2 pi over 3 such that the theta value is positive. We're starting with an angle of pi over 3. And if we want our point to have a positive value of theta, that means that our r value has to be negative. Measuring from the positive x-axis, that tells us we should add pi to pi over 3, giving us theta equal to 4 pi over 3, giving us the point negative 3/2, 4 pi over 3. Same idea on the next example. We're starting with theta equal to 5 pi over 3. And since we know that we're looking for a positive theta value, that tells us that our r value has to be negative. Negative r extending through the origin in the opposite direction gives us theta equal to 2 pi over 3. In both of these last two examples, we've described the same point 2 different ways. This will be very helpful as we're moving into finding the intersection of polar curves and area between polar curves. So we'll come back to this in the next example. We want to find all the points of intersection between the two curves, 1 plus cosine theta and 3 cosine theta, when theta is between 0 and 2 pi. When you're looking for the intersection of curves, you should start by plotting all of the intersection points on the graph. We can see 2 intersection points, one in the first quadrant and one in the fourth, and the curves also intersect at the origin. To find where the curves intersect in the first and the fourth quadrant, we want to set our 2 equations equal to each other and then solve for theta. 1 plus cosine theta is equal to 3 cosine theta. Subtracting cosine theta from both sides, we have that 1 is equal to 2 cosine theta. That gives us cosine theta equal to 1/2. And solving for theta, we have that theta is equal to pi over 3 and 5 pi over 3. When we sub theta into either one of our curves, we find that r is equal to 3 halves. In the first quadrant, that gives us the point 3 halves pi over 3. Since red and blue make purple, I thought I'd write this point in purple. In the fourth quadrant, we then have 3 halves 5 pi over 3. Next, we need to know where each of these curves go through the origin. To do that, we need to set each one individually equal to 0, starting with 1 plus cosine theta equal to 0. We have cosine theta equal to negative 1. And solving for theta, we have that theta is equal to pi. Going over to our sketch, we can label the point 0 pi. Setting our second curve, 3 cosine theta, equal to 0, we can multiply through by 1/3, giving us cosine theta equal to 0, which means that on the interval between 0 and 2 pi, theta is equal to pi over 2 and 3 pi over 2. Labeling our graph, we have 0 pi over 2 and 0, 3 pi over 2. 2 points should make us think twice, though. It looks like the circle only goes through the origin once, but from last week, we know that we can go all the way around the circle one time when theta is between 0 and pi, and a second time from pi to 2 pi. That means that for the circle r equal to 3 cosine theta, we should go through each point of intersection once when theta is between 0 and pi, and then a second time when theta is between pi and 2 pi. From our warm-up, we know that 3 halves pi over 3 is the same point as negative 3 halves 4 pi over 3. And we also found that the point 3 halves 5 pi over 3 is the same as negative 3 halves 2 pi over 3. That tells us that the curves also intersect when r equal to 1 plus cosine theta is at the point 3 halves pi over 3, and our second curve, r equal to 3 cosine theta, is at negative 3 halves 4 pi over 3. This is in the first quadrant, and not forgetting about our fourth quadrant, when r equal to 1 plus cosine theta is at the point 3 halves 5 pi over 3, and r equal to 3 cosine theta is at negative 3 halves 2 pi over 3. Big picture, that means that these two curves can intersect at different values of r theta. Knowing how to find the intersection between two curves is essential to finding the area between the two curves. We know in calculus, when we're in Cartesian coordinates, we can find the area between the curve and the axes by breaking the region up into rectangles. In polar, we don't have rectangles, so we can find this area by breaking the region up into sectors. Sounds easy enough, but we might want to review how we find the areas of sectors before we dive into integrating. Back to geometry. Let's say that we have a circle with a radius of r and an angle of alpha. We know that when you go around the entire circle, that's 2 pi radian. So alpha is out of a total of 2 pi radian, which means that the shaded part of the sector is alpha over 2 pi of the whole circle. The area of a sector is going to equal this portion of the circle, alpha over 2 pi, times the entire area of the circle. Subbing in for the area of a circle gives us alpha over 2 pi times pi r squared. The pi's cancel out, leaving us with 1/2 r squared alpha. How can we apply that to polar curves? Now, instead of r being the distance from the circle to the center of the circle, we now have that r is equal to f of theta, the distance from the curve to the pole, and alpha is equal to d theta. In terms of our polar curve, r equal to f of theta, the area of this shaded sector is 1/2 r squared d theta. That's just the area of one sector. If we want the total area, then we need to add up all of the sectors between theta equal to a and theta equal to b, giving us the integral from a to b of 1/2 r squared d theta. That means anytime we're integrating in polar coordinates, we need to use this formula. Let's try an example. We're looking for the area in the first quadrant inside the cardioid r equal to sine theta minus 1. This is the same curve from our warm-up exercise. Our intuition tells us that since we're in the first quadrant, theta should be between 0 and pi over 2, but you always have to check the sign of r. From our warm-up exercise, we know that r is always going to be less than or equal to 0 for this curve, sine theta minus 1. And so if we want the area in the first quadrant, we have to use opposite angles for our bounds. Another easy way to check this is just plug in theta equal to 0. Curves always start at theta equal to 0. Sine of 0 is 0 minus 1 tells us that at theta equal to 0, r is -1. -1 pushes us through the hole, giving us the point -1, 0. We know that curves always go in the counterclockwise direction, telling us that when theta is between 0 and pi over 2, our curve is in the opposite quadrant. Just a quick, easy way to confirm your answer. To find our area, we have that area is equal to 1/2 the integral from pi to 3 pi over 2 of r squared, where r is equal to sine theta minus 1 d theta. This is equal to 1/2 the integral from pi to 3 pi over 2. Foiling sine theta minus 1 gives us sine square theta minus 2 sine theta plus 1 d theta. To integrate sine squared theta, we need to use our half angle identity, that this is equal to 1/2 times 1 minus cosine 2 theta. Subbing that in, we have 1/2 the integral from pi to 3 pi over 2 of 1/2 times 1 minus cosine 2 theta minus 2 sine theta plus 1 d theta. To make the algebra a little easier, let's distribute this 1/2, and then we'll add the 1/2 plus 1, giving us 1/2 the integral from pi to 3 pi over 2. 1/2 plus 1 is 3/2 minus 1/2 cosine 2 theta minus 2 sine theta d theta. Integrating with respect to theta gives us 3/2 theta minus 1/4 sine of 2 theta plus 2 cosine theta from pi to 3 pi over 2. Evaluating our bounds, when theta is equal to 3 pi over 2, we have 9 pi over 4 minus 1/4. 3 pi over 2 times 2 gives us 3 pi, and sine of 3 pi is 0. Cosine of 3 pi over 2 is also 0. Subbing in our lower bound of pi, we have 3 pi over 2. Sine of 2 pi is 0, and cosine of pi is -1 times 2 gives us -2. This is equal to 1/2. We have 9 pi over 4 minus 3 pi over 2. 3 pi over 2 is equal to 6 pi over 4. So 9 pi over 4 minus 6 pi over 4 gives us 3 pi over 4. Minus a -2 gives us a +2. Distributing our 1/2 out front, we have 3 pi over 8 plus 1. Just a quick reminder to always leave your answer as an exact answer. Because our formula for finding polar area is 1/2 r squared, and in polar we're generally in terms of sine or cosine, you'll end up needing to use these half-angle identities quite often. So far in our examples, we've only been working with one curve. When we're looking for the area between polar curves, it still works based on the same principles. I've tried to break it up for you into smaller, manageable pieces, walking you through it step by step. If you need to graph the curves, then you should always start there. For your homework and for exam questions, we won't ask you to graph a curve. It would be set up in the same way as this one, except for it'd be all in black and white. You always have to check the sign of R. We're looking for the area that is inside both of these curves. Make sure you begin by identifying the correct region. If there's any symmetry, you should definitely take advantage of it. These are the same curves from example 1, so we know using symmetry is going to simplify this problem quite a bit. That means when we're looking for this area, we can just find the area in the first quadrant and multiply it by 2 to find the total area. If the curves were completely in black and white, then I would use my red pen and my blue pen to highlight the boundaries of the region for each curve. But since I already identified each curve by color, I'll instead use a highlighter. The idea here is that any part of the curve that's touching the shaded yellow area should be highlighted. This next step is one of the most important and overlooked steps of the whole process. We want to draw lines from the curve to the pole, but only along the highlighted portions of the curve. And we want to do it in corresponding colors. For r equal to 1 plus cosine theta, our curve in blue, I'll start at the intersection point and draw a line from the intersection point to the pole, and then I'll continue to sketch in lines from the pole to our highlighted area. For our circle, r equal to 3 cosine theta, I'll repeat, now using my red pen. Let's divide up this problem into two smaller, simpler problems. This area that we're looking for is equal to 2 times. Now let's just focus on the curve in red, r equal to 3 cosine theta. For just that curve, we're looking for the area of this slice. Then we want to add the area of our region highlighted in blue. We have the 2 out front because of the symmetry. To find our bounds, we need to know where each of these curves begin and end. I'll use an S for where our curve starts. Since polar curves go in the counterclockwise direction, 3 cosine theta is going to start at the intersection point. It moves in the counterclockwise direction and ends at the origin. For our cardioid, knowing that our curve has to move in the counterclockwise direction, we start at the horizontal axes and we end at the intersection point. Let's start by finding our intersection point. To find our point of intersection, we set r equal to r. Subbing in for our formulas, we have 1 plus cosine theta equal to 3 cosine theta. Subtracting cosine theta from both sides, we have 1 is equal to 2 cosine theta, which gives us cosine theta equal to 1/2. And solving for theta, we have theta is equal to pi over 3, 5 pi over 3. And we could go on, but we're only concerned with the first quadrant. Since we're restricting ourselves to the first quadrant, we only want the theta value that falls in the first quadrant. Since both of these curves are going to be positive when we're in the first quadrant, we don't have to worry about opposite angles, which means we'll use theta equal to pi over 3 as our intersection point. Next, we need to find where 3 cosine theta intersects the origin. To do that, we set r equal to 0. 3 cosine theta is equal to 0 when cosine theta is equal to 0. Theta is equal to negative pi over 2, pi over 2, 3 pi over 2, and you could keep going. But looking back at our sketch, we want the intersection point with the origin that occurs directly after pi over 3, which tells us that theta is equal to pi over 2. We can label those values on our sketch. Theta equal to pi over 3 is where our curve is starting and ending at theta equal to pi over 2. For the curve 1 plus cosine theta, we've already found that intersection point. So we know that the curve will end at theta equal to pi over 3. And we want the horizontal value that occurs right before pi over 3. The only time that our curve is going to cross the horizontal axes is when theta is equal to 0, pi, 2 pi, and so on. And since we want the one that is directly before our point of intersection, we want to let theta equal 0. Setting up our integral to find the area, we have that our area is equal to 2 times 1/2 the integral. We can look at our sketch above to find our bounds. We went from pi over 3 to pi over 2. So we have the integral from pi over 3 to pi over 2 of 3 cosine theta, quantity squared, d theta, plus 1/2 the integral from 0 to pi over 3 of 1 plus cosine theta, quantity squared, d theta. Anytime you are using symmetry, you should definitely note it as part of your answer. As you can see from this example, the majority of the work was in finding the bounds. So When you see this type of problem on homework or an exam, know that the bulk of the credit will be given for finding the correct bounds. In this example, we found the total area by adding two separate areas together. Let's look at an example that involves the difference between two areas. Here, we're looking for the area that is inside 2 sine theta, that's our circle, but outside 2 minus 2 sine theta, that's the cardioid. To get a general idea, I'll just quick highlight this area in yellow and then reread the problem one more time to be 100% positive that we are finding the correct area. We are inside the circle and outside the cardioid, so we've shaded correctly. We can also identify the symmetry. These curves are symmetric over the vertical axes, which means that we can focus on just the first quadrant, find that area, and multiply it by 2 to find the total area. Because of that, when I'm highlighting my boundaries, I'm only going to focus on the first quadrant. We highlight the portion of the curve that lies directly on this region. We want this part of the curve in blue for the circle, and the part of the curve for the cardioid, 2 minus 2 sine theta, that touches the highlighted region, looks like this. For our next step, we want to draw lines from the highlighted portion of the curve to the origin. So starting in red with my cardioid, our lines look like this. And in blue, drawing from the curve to the hole, we can see that we're overlapping the area we had already drawn in red. Because we have overlap between these regions, we know that our total area is going to involve the difference between our region in red and our region in blue. Just like we did in the previous example, let's set this area up as the difference of two easier areas. We'll multiply by 2 out front because of the symmetry. And just doing a quick sketch for our circle, 2 sine theta, our region looks something like this, where we're starting at the intersection point. We move in the counterclockwise direction, and we end at the vertical. And from this, we subtract the area in red. I'm not going to draw this perfectly to scale because I just want it to be a little bit bigger so we can better identify the regions we're working with. So the basic idea is that we're looking for the region that looks something like this. Knowing that our curve moves in the counterclockwise direction, we're again starting at the intersection point, but here we will end at the origin. To find our intersection point, we set r equal to r. Subbing in for r, we have 2 sine theta equal to 2 minus 2 sine theta. Adding 2 sine theta to both sides, we have 4 sine theta is equal to 2. Dividing through by 4, we have sine theta is equal to 1/2, which means theta is equal to pi over 6 and 5 pi over 6. Since we're restricting ourselves to the first quadrant, we only want the theta value that falls in the first quadrant. Since both of these curves are going to be positive when we're in the first quadrant, we don't have to worry about opposite angles, which means that theta equal to pi over 6 lies in the first quadrant, and 5 pi over 6 lies in the second quadrant. Let's label pi over 6 on both of our sketches above, starting at theta equal to pi over 6 for our circle and the cardioid. To find where our circle ends, we need to know when the curve intersects the vertical axes. That's always going to be at theta equal to pi over 2, 3 pi over 2, and so on. And we're looking for the one that is directly after our point of intersection, pi over 6. So the very next vertical theta value after pi over 6 is pi over 2. That means our curve 2 sine theta will end at theta equal to pi over 2. To find where our cardioid ends, we need to know when 2 minus 2 sine theta intersects the origin, which means we should set r equal to 0. 2 minus 2 sine theta is equal to 0. Adding 2 sine theta to both sides and then dividing by 2, we have sine theta is equal to 1. Sine theta is equal to 1 at pi over 2, 5 pi over 2, and you could keep going. But we're looking for the one that occurs directly after the intersection point, which is theta equal to pi over 2. Let's label that on our sketch above. Now we have all of the information to set up the integrals that give our area. We have that the area is equal to, let's note that we're using symmetry with the 2 out front, 2 times 1/2 the integral from pi over 6 to pi over 2 of 2 sine theta, quantity squared, d theta, minus 1/2 the integral from pi over 6 to pi over 2 of 2 minus 2 sine theta, quantity squared, d theta. And that's our final answer. In this example, we're looking for the area that lies inside the inner loop of 6 cosine theta minus 3. Instead of looking for intersection points between curves, like we did in the last examples, we need to know where this curve goes through the origin. We know that curves always go through the origin when r is equal to 0. Setting 6 cosine theta minus 3 equal to 0 gives us cosine theta equal to 1/2. Theta is equal to pi over 3 and 5 pi over 3. Just because we've found 2 theta values where our curve goes through the origin does not necessarily mean that pi over 3 less than or equal to theta less than or equal to 5 pi over 3 gives the inner loop. It could give the inner loop, but it's also possible that when theta is between pi over 3 and 5 pi over 3, it gives the outer loop instead. A quick way to check this is to look where our curve starts. Curves always start at theta equal to 0. Subbing that in gives us r is equal to 6 times cosine 0 minus 3. Cosine 0 is 1, and so 6 minus 3 is 3. That all by itself is not very helpful because we have no scale on this graph. So we don't know if theta equal to 3 occurs here or here. But we do know that one of these points will also correspond to theta equal to pi. So let's plug in theta equal to pi to find our r value. R is equal to 6 times cosine pi, cosine of pi is -1, minus 3, which gives us -9. Theta equal to pi corresponds to this part of the axis, but because our r is negative, it pushes us through the origin to positive 9, meaning this point on the curve corresponds to negative 9 pi, and on the inner loop, this point is 3, 0. Knowing that our curves start at theta equal to 0 and move in the counterclockwise direction, our curve will move through the origin at theta equal to pi over 3, then along the outer portion of the curve until finally coming back to the origin once again at theta equal to 5 pi over 3, where it passes through the origin until our curve finally ends at theta equal to 2 pi. If we wanted to find this area without using symmetry, then we start at theta equal to 0 and go to pi over 3, giving us this portion of the area. And for our second integral, our bounds would be from 5 pi over 3 to 2 pi, corresponding to the area shaded here in orange. Of course, it's always easier to use symmetry when you can, and so if we just were looking at the first quadrant, we'd have the integral from 0 to pi over 3 of 6 cosine theta minus 3 quantity squared, half of that, and then because of the symmetry, we multiply by 2. There's all kinds of fun variations you can do on this problem, finding different areas. And you'll do one similar in workshop tomorrow, where you're looking for the area between the inner loop and the outer loop. I wanted to revisit finding the points of intersection of polar curves and highlight some of the more challenging examples. We use the same process that we used on the earlier examples. So let's begin by graphing the curves if they aren't already graphed for you. Here they are. And then plot all of the points of intersection. Here it looks like we have 2 points of intersection, one in the third quadrant and one in the fourth quadrant. We know that curves intersect when r is equal to r. Setting our curves equal to each other, we have 4 sine theta minus 4 is equal to 2. Let's add 4 to both sides, giving us 4 sine theta is equal to 6. Solving for sine theta, we have sine theta is equal to 3/2. We know that the range of sine theta has to fall between -1 and 1. There are no theta values that we could use that would give us back sine of theta equal to 3/2. But clearly, we can see that there are 2 points of intersection. So how do we find these 2 values? Thinking back to last week's lecture, where we graphed the circle r equal to 2, we had said that r equal to 2 gives the same circle as r equal to -2. So let's set 4 sine theta minus 4 equal to -2. Solving for theta, let's add 4 to both sides, giving us 4 sine theta is equal to +2. Sine theta is equal to 1/2. Solving for theta, we have that theta is equal to pi over 6 and 5 pi over 6. That gives us our points of intersection as -2 pi over 6 and -2 5 pi over 6. Both of these points give us first or second quadrant angles, but third or fourth, respectively, quadrant points. The takeaway from this example is that for any function f of theta equal to r, we know that r theta and negative r, theta plus pi, indicate the same point. So you can replace one of the equations with negative r equal to f of theta plus pi and repeat step 1. Here, we replaced r equal to 2 with r equal to negative 2, and we're able to solve for our points. Let's do another example along similar lines. For our last example, instead of looking at the points of intersection involving a circle, let's find the points of intersection between two cardioids. Looking at our graph, we can see 3 points of intersection. One is in the first quadrant, another intersection point in the third quadrant, and then they intersect at the origin as well. Let's start by setting r equal to r. Subbing in, we have cosine theta minus 1 equal to sine theta plus 1. Let's subtract sine theta from both sides and add 1 to both sides, giving us cosine theta minus sine theta equal to 2, which means there are no solutions to this equation. And so setting r equal to r does not give us back any intersection points. Let's jump down to step 4 then. By step 4, we know that negative r is equal to cosine of theta plus pi minus 1. Gives us the same curve as r equal to cosine theta minus 1. Cosine theta plus pi is equal to negative cosine theta. You can either use the sum formula, or you could look at the unit circle. If we have an angle of theta, then cosine theta plus pi gives us the same value as cosine theta. In place of cosine theta plus pi, let's substitute in negative cosine theta. Our equation becomes negative r equal to negative cosine theta minus 1. Multiplying through by negative 1, we have that r is equal to cosine theta plus 1. Using this equation, let's try setting r equal to r and see if we can find any intersection points this way. On the left-hand side, we have cosine theta plus 1 equal to sine theta plus 1. We can subtract 1 from both sides, giving us cosine theta equal to sine theta. Dividing both sides by sine theta, we have tan theta is equal to 1, giving us theta is equal to pi over 4 and 5 pi over 4. Let's sub our theta values into r equal to sine theta plus 1. At pi over 4, we have 1 plus the square root of 2 over 2. And at 5 pi over 6, our r value is 1 minus the square root of 2 over 2. For both of these points, we know that our r values are greater than 0, which tells us that our points map into the same quadrant as the theta values. Plotting those points, we have, if we sub our theta values into r equal to cosine theta minus 1, at pi over 4, we have negative 1 plus the square root of 2 over 2. And at 5 pi over 4, we have negative 1 minus the square root of 2 over 2. In both of these cases, our R value is less than 0, telling us that our points map into the opposite quadrant as their theta values. Labeling our graph, we have telling us that while our curves intersect, they are intersecting at different points for each one of them. We have one more intersection point, and that is at our origin. Let's set r equal to 0 to find where each of these curves intersect the origin. For cosine theta minus 1, we can add 1 to both sides, giving us theta equal to 0 and 2 pi, setting sine theta plus 1 equal to 0. Let's subtract 1 from both sides, giving us sine theta equal to negative 1. Solving for theta, we have theta equal to 3 pi over 2. That tells us that the curves intersect at the origin when cosine theta minus 1 is at the point 0, 0, and also at the point 0, 2 pi, while sine theta plus 1 intersects the origin at 0, 3 pi over 2. If you were looking for any combination of areas between these curves, you would have to be very careful about your bounds on both of your integrals, since they don't line up at any point for either of the two curves.